Modern global telecommunications rely on the transmission of electromagnetic waves. Whether moving through fiber-optic cables or open air, information travels via oscillating electric and magnetic fields. These waves interact with everything they touch. When a radio signal encounters dense matter, like rock, seawater, or reinforced concrete, it is reflected, absorbed, or scattered. A Faraday cage makes this block absolute. By redistributing electrical charges along its exterior shell, a conductive shield cancels out incoming fields, ensuring no data reaches the interior. Circumventing this requires a carrier that does not interact with the electrical properties of matter. Because all observed mass is positive, there is no known material that can shield, reflect, or absorb a gravitational field. A change in a local gravitational field propagates through rock and metal as easily as it does through a vacuum. However, the gravitational coupling constant is approximately 40 orders of magnitude weaker than electromagnetism. This weak coupling defines a steep engineering trade-off. Gravity allows for unblockable propagation, but detecting those signals requires the sensitivity of a LIGO observatory, massive kilometer-scale vacuum tubes designed to catch the ripples of colliding black holes. Researchers have spent decades searching for ways to generate detectable signals without relying on astronomically massive objects. One proposal, detailed by Gary Stevenson, suggests using dissimilar superconducting Josephson junctions on a microchip to force high-frequency gravitational transitions. This line of thinking is mirrored in military patents filed by Salvatore Pais, which use mathematical models of vacuum polarization to theorize propulsion and communication. These chip-scale designs rely on spin-2 quantum transitions that have never been observed in a laboratory. To date, none of these devices have produced a validated gravitational signal. The first successfully verified gravitational communication link bypassed quantum engineering and high frequencies entirely. It relied instead on the simple, macroscopic physics of moving a very large, incredibly heavy object back and forth. This experiment used a common elevator counterweight, an 1,800-kilogram block of steel, as an active gravitational antenna. Moving this counterweight up and down a shaft shifts the static local gravitational field, providing a measurable signal without the need for high-frequency radiation. By applying Newton's law of universal gravitation, the team could map the mass as it moved from floor Z0 to floor Z1. This vertical transit changes both the magnitude and the direction of the gravitational acceleration vector, acting on a fixed sensor. Maximizing this change requires the mass to traverse a distance roughly equal to the total transmission length. Isolating the vertical component of the signal reveals a theoretical peak shift of 50 nanometers per second squared. This 50 nanometer per second squared shift is a tiny fraction of Earth's total gravity, requiring an 1,800 kilogram mass to travel 5.5 meters just to generate the fluctuation. By mathematically isolating this specific vertical vector, a local gravitational anomaly can be resolved into a binary data bit. Mathematically, this system acts as a gravitational dipole antenna. These polar plots show how the gravitational field distortion changes as the radial distance from the mass increases. While an electromagnetic dipole has zero transmission perpendicular to its lobes, a gravitational antenna maintains 25% of its maximum strength in those same directions. Electromagnetic signals decay at a rate of 1 over r. The signal from the static mass dipole decays much faster, scaling at 1 over r cubed. This inverse cube decay makes it difficult to maintain a link over any distance greater than a few meters. The maximum data rate for this channel is governed by the Shannon-Hartley theorem. This curve plots channel capacity on the y-axis against the integration time required for the sensor on the x-axis. Two variables limit the total capacity: the transit time of the counterweight, t, and the sensor's integration time, tau. Resolving gravity signals faces a persistent signal-to-noise problem. Because environmental noise is Gaussian, the sensor needs long integration periods, often 40 seconds or more, to resolve a single bit of information. The channel reaches its theoretical limit when the integration time matches the time it takes the mass to move. This means gravitational data rates are not limited by frequency bandwidth, but by the physical velocity of the transmitter. To test this in a controlled environment, the researchers separated their gravimeter and the 1,800 kilogram mass with a solid brick wall. They transmitted a 49-bit message across 0.7 meters at a rate of exactly 1 bit per minute. This signal sequence chart shows the raw data. As the cursor sweeps across each 60-second window, we can see the gravitational shifts rise above the noise floor. By setting a threshold, each window is resolved into a binary 1 or 0. These binary strings are then grouped into 7-bit blocks and translated into standard ASCII text, revealing the word gravity. This successful readout is the first empirical proof of unblockable, zero-line-of-sight communication using classical hardware. A fast single-shot measurement with this equipment results in a bit error rate of 0.01. Applying a 25-second data integration window reduces that averaged error rate to 10 to the negative 9. This 10 to the negative 9 rate meets the reliability standards required for modern fiber-optic networks. However, scaling this communication range is difficult. If the counterweight were replaced by a 75,000-kilogram mass, the weight of a Challenger 2 tank, the theoretical signal would be stronger. Pairing that mass with a superconducting gravimeter would increase sensitivity down to 0.01 nanometers per second squared. Even with these extreme upgrades, the inverse cube decay rate limits the effective communication range to roughly 500 meters. For comparison, electromagnetic signals routinely transmit data across the vacuum of space to the Voyager spacecraft, billions of kilometers away. Gravitational communication is an engineering reality, but it remains confined to a specific niche, low-bandwidth environments where every other signal is blocked.